slide. So I'll try to present my own slides in a decent way. So I'm going to talk about
Sofie, can you wear a microphone, or can I just give you
this one?
Yeah, this one if you can, or you can just hold this one.
Okay, is this good? Yeah, sorry. So I will try to present my own slides, and I'm going to talk about massive integrated communication and sensing. So we're going to start a bit from massive MIMO and then also move on to cell-free MIMO. We've seen some presentations on this already this morning. So I'm going to present some work done by some people from my team. So the first thing I'm going to present was work done by Ali. He graduated in 21, so already several years ago, but I think he was one of the first to do integrated communication and sensing, although we called it at that time RATCOM. Then I'm going to present some work by Andrea and Siberen, who worked on the massive MIMO a little bit, and then some recent work by one of my PhD students at IMEC in collaboration with André Bordeaux, and they're doing a lot of interesting work on cell-free integrated communication and sensing. So we've seen this already in 6G. Integrated communication and sensing is one of the new usage scenarios. So this is interesting, right? Because we've been working on this for many, many years. And we can imagine many different use cases. And this makes it a bit tricky because of the variety of use cases. There's also a variety of algorithms, architectures, and things that we can do. We can go to terahertz sensing, we can do RIS. And depending on the use case, of course, a very different metric algorithm approach will be needed. So here I put some use cases, and here I put another slide where we see what are the main drivers for 6G. And you see that there are autonomous vehicles, health monitoring, and Industry 4.0. So although I will present today conceptual work that could be applied to any of these use cases, I agree with what Alain presented before. Probably academia should also do a little bit more effort to understand these application scenarios to make sure we're doing the right things that will eventually result in something used in industry. But I'm not going to talk about that today. But what I wanted to show still related to that is that IMT, they have done their work already on putting forward this hexagon of the new usage scenarios. And they have also done some effort already in translating that to the capabilities for IMT 2030. And here you see the enhanced capabilities, which were just evolutions of things we already know from 5G. And then above, you have the new capabilities. And if you want to understand them, coverage, I think, is still possible to understand, but then you have sensing-related capabilities, AI-related capabilities, sustainability, and interoperability. And compared to these metrics, you see that they are much less defined and quantified. Luckily, there is one metric already quantified, and that's positioning. So I'll start working on this metric, but it will be needed to also quantify these metrics at some point to be able to know what you want to do there. Okay, so we need to translate all these metrics to what we really want to do. So far, only one metric is defined, localization, and we need to do it very accurate, 1 to 10 centimeters, but at least we can work on this one already now. I'll come back to that image later, just be prepared. So if we want to localize users, 10 centimeter accuracy. So we can do it in two ways. We can do it using an active transmitter. Where is the pointer? An active transmitter, so the user is transmitting a signal, and we have an infrastructure around that is trying to localize the user. Or you can also do it in a passive way. We have transmitters and receivers around us, and we try to localize reflections on a user. I'll first talk about, of course, we can also add risk in the environment. But I'm not going to talk about that, but it seems to be a hot topic these days to do that. And what we're going to do is to try to localize the user. Okay, first thing, active localization of users. And for that, we started from a massive MIMO deployment. So this is a measurement that we did in my lab. And here you see, if I have one antenna. So what we did is we put in an environment like that, position us on the floor, that were measuring every few millimeters the received signal strength. And here you see the channel actually, so the amplitude of the channel, if we have only one transmitter active, so it looks like that. I think you can understand what is being shown there. And here you see exactly the same, but we have 64 antennas active, and they are beamforming to the user. And what you see here is actually in radar terminology, the ambiguity function when you're doing match filtering on the target position of the user. Here you see it inactive. Actually, it's actually maximum ratio transmission towards user. So what do you see? If you're working in a near field with many antennas, you not only have a beam, you have a spot, and the spot has a certain elliptical shape, right? And that gives you localization performances in the end. So here you see that the localization performance is not super accurate. Like if you would work on this ambiguity function, you see you have a few degrees here, but the localization precision and the depth is not, because of the wavelength and the fact that we have antennas located here, not super good. So this is another view of the same measurement system. So we did that with the antenna here, a ULA, URA in a square, or in a self-free kind of setup where we distribute the antennas around. And here you see the positioners where we can position the antennas millimeter by millimeter to verify what we are doing. And then, of course, a lot of software needed to automate this, but I'm not going to talk about that. So what we did is the same measurement. Instead of putting it into a maximum ratio transmitter or matched filter, we put it in a deep neural network, not even a complicated one. I'm not going to explain it to you, but the main message is that from our channel database, we could get to positioning information that is much more accurate than the ambiguity function we saw before. Actually, in our setup, we could get below 1 centimeter accuracy, which is surprising given the wavelength and the bandwidth of our system. Good. Based on that, we explored also some other methods. For instance, we compared end-to-end learning, where we put everything in a big neural network, to near-field music, where we also explored using AI to calibrate music. We used all kinds of metrics. For instance, ML music is music, but with some kind of fully connected network before. That is some pre-processing mainly to do the calibration of the array, etc. We put that all together, and here you see, I don't want to talk too much about this. I want to go to the massive MIMO one, but the main message I wanted to bring to you is here you see our near-field music, right? So this is positioning error in millimeter, and our near-field music is really the best. So why do we need 100 samples to calibrate our near-field music? We just needed it because our antenna array was not calibrated. We use 100 measurements to calibrate it in the room. And with that in the room calibrated antenna array, near-field music gives us a very, very good result, not even using machine. And why do we get it? Because it's near field. So every measurement not only gives us angle, but also some kind of distance, right? That's what near field music is. AI also does more or less good, but never as good as near field music. So don't think AI can solve everything. And here we see that the distributed variant of music is close to near field music, but you need 50,000 training samples, which is a lot. And it's still not as good as near field music. But what is the benefit of this one? The computational complexity is much lower. So if you go here to near field, central near field music, it's really computationally complex. So AI can help, but in my view, mainly to reduce the compute cost, not so much to improve the performance. Okay, where are we now? We are now here. In the story, we can localize our user with massive MIMO, but the user was still having an antenna, right? So now what we want to do is, can we also localize a user that is not having an antenna? And I'm not going to talk about machine learning anymore, just using match filtering and algorithms. So if we want to localize our user, we're going to have a system that is doing integrated communication and sensing. I don't have to introduce that here to the room. I just wanted to introduce that I'm going to explore several methods. People can do bistatic sensing, so you have a transmitter and a receiver, and you measure the reflections. We can do monostatic sensing or some full-duplex kind of sensing, or you can do multistatic where you have many transmitters and receivers. So I will be going between all these kind of methods in the next phase of my presentation, so you have them in your minds now. The first thing I'm going to do is just monostatic sensing. I send a signal and receive it back. And that's the most simple thing to do. So this is something we did already 8 years ago, actually. So at that point, we were working on full-duplex communication, nothing related to radar. And we had here an antenna. We had a very simple electrical balance duplexer, and we had a software-defined radio that was sending and receiving signals at the same time. And the problem that we had at that time was self-interference. So I draw here 2 antennas, but although there is only 1 antenna, but you should see it as we send a signal and we receive a signal at the same time. And this transmitted signal is 100 dB stronger than the received signal. And we have leakage in the hardware, but we have also leakage over the air if we would have 2 antennas. And we also have self-interference from reflections in the environment, right? So at that time, we spent a lot of time making algorithms to eliminate these reflections in the hardware, over the air, and from the environment. So we made actually an adaptive filter that can learn all these reflections, so we can subtract them from our received signal. And then we said, this adaptive filter, actually these weights represent dynamic variations in the environment, so we can easily do Doppler processing on top of them and use them for sensing. Voila, here you see it in action. So this is the same electrical balance duplexer, same antenna with a software-defined radio here. Very narrow band signal. To people in my team, this is Hadden, by the way. And they're just walking, and you see that indeed this very simple adaptive filter for interference cancellation can be used for range Doppler processing. And also here you see the Doppler resolution is not so bad, but the range resolution is quite horrible because it's a very narrow band system. Good, that was interesting. So then we at that time started to be convinced that actually it is relatively easy to do sensing if we have communication signals. So we said, okay, we can do sensing with communication signals with OFDM. And we have our massive MIMO testbed. Before I go to the testbed, just one more thing. For this specific implementation, we made it on the FPGA because we needed to be very fast to do the self-interference cancellation. We had a system where we only do the filter for communication. And then the implementation where we added a little bit of logic to do the Doppler processing, nothing fancy, but it's just to make them up that you show. And we saw that actually we did not need a lot of extra resources on the FPGA. So at that time we thought, this comes for free from our communication processing. Let's do more radar. I'll come back to that later. This was a bit too optimistic, I think. And now we're starting to be convinced that if you want to do very good radar processing, sometimes it can be quite costly. But in this setup, it was actually quite cheap. Depends also a bit on the constraint and how you want to do it. So at that time, we said we can do sensing. Let's apply it to our massive MIMO system, right? So here we have a simulation in this case. We have our massive MIMO linear array here. And we did something in it. We added here 4 UVs in the middle of our base station. So we cut the base station in 2. We put 4 user equipment antennas in the middle. And we use this as some kind of monostatic massive MIMO array. And here we're computing the ambiguity function by processing all the signals. So we have a lot of signals to process. because we have a lot of, we have a lot of transmitters for, in this case, for UV, we have 64 receivers. We send 640 symbols, frames, you could see it. So that's every frame is sent, so two per millisecond. And then we also have a lot of subcarriers, K. So that's a lot of things to compute, and your ambiguity functions there, up written there. That's what we use to analyze the performance of our radar. And here you see the results. So with this system, OFDM on these parameters, you could detect two targets relatively close to the array and with quite a good resolution. I'll come back to the resolution later, but this is what our simulation told us. And the most interesting message I want to bring here, and that surprised us at that time, was look at the ambiguity function for one subcarrier versus 400 subcarriers. It's different, but even with one subcarrier, which has 0 bandwidth, even with one, and at that time, people were still convinced if you need to do good range resolution, you want to achieve a good range resolution, you need a lot of bandwidth. And here we showed that if you have a massive MIMO array, even with only one subcarrier, 0 Earth bandwidth, you can resolve two targets in the near field. That was something that surprised us at that time. And then we said, okay, let's verify it in measurements, because nobody trusts models except the people who model, and everybody trusts measurements except the people who measure, right? So we try to confirm it. So we built this whole array exactly the same. So here you see the 64 antennas of our base station and 4 in the middle, or connected through the user equipments. You cannot see it here. These are just these cables that go to the UVs. And here we have a little cam, right? And we cheated a little bit. We put some absorbers and everything around. We have also measurements without the absorbers, but the absorbers are kind of useful, right? From this measurement, the thing that you should see, if you have one transmit antenna, one receive antenna, your bistatic range resolution is 17 meters, which is much larger than the size of the room, right? And with this range resolution, we want to localize a can of a few centimeters. That's a bit what we want to do. And we have also from our parameters and Doppler resolution, etc. So voila, this came out of the measurements. And first thing to see is pretty similar to the simulations, right, that we did before. And so this was a theoretical ambiguity function on the left. And then two ways of doing the back projection, because yeah, you have a lot of things to combine together, a lot of signals to combine together, and you can do that coherently or partially coherently, and there's different ways of doing it. Based on the algorithm used, the difference is not big, only in the side lobes you see some differences. You pretty much see back our target. So we could detect the can, and we have a much better resolution in X than in Y. Good, nice. If you want to read more about the paper, I refer to this paper. I'm not going to explain everything in detail here. I actually also don't know how much time I have. And from this measurement, you see, wow, we can get good resolution. Here was with 20 megahertz of bandwidth, but our antennas give us really a range resolution improvement. And the shape looks elliptical, but how to quantify it? And we were interested in coming up with a way to compute this resolution for generic configurations. So then so what is radar resolution and accuracy? So the resolution is, what is interested for radar is the resolution in which you can detect the targets, and also the difference between targets you can detect. for instance, the range resolution and angular resolution, or resolution in X and resolution in Y. So there's difference of them. You also have the accuracy of the parameter estimates, and typically there's a relationship. For instance, for an FMCW radar, accuracy and resolution are related using this equation. And we want to do this in a generic way, but for different types of measured parameters, for instance, range, angle, XY location, etc. They're often coupled and spatially variant. So it could be that your range resolution, and I have shown before, I did not mention it, could be different here than here. It's the same array, but because of the spatial coupling, sometimes closer to the array have a better resolution than further away from the array. So how to quantify that and come up with a metric? And a resolution is typically measured using this matched filter response ambiguity function, accuracy typically using Monte Carlo simulations. So could we come up with a rule of thumb like this one for generic radar systems that you can compute it easier? So that's what we try to do in this paper here. We propose a generic way of doing it, and for a class of exponential signals, we have developed it a bit further. So here are our exponential signals. We have measurements, the samples n, and we have a set of parameters that we want to determine, angle, etc. We compute a matched filter response as function of the parameters, and then we define a parameter which is the half power. Bandwidth is wrong. I was a bit too tired when I made the slide beam width, sorry. And it's defined as you take the maximum of the matched filter and then you look in which parameter change you need to do to have only half of the maximum. So you want to see, okay, 1 meter in X, 2 meter in Y, or that much degrees and angle, etc. So can we compute it? So we came up with a way of computing it. I'm not going to go into all the details, I put here some equations just to show we have closed form expressions, a wide range of them. But if you want to read the details, please go to the paper because it's too much to present here. But for instance, for a half wavelength uniform MIMO array, this is the result in 1 dimension. I have some results in the next slide for multiple dimensions because that's what you're after. But this is to show that from our method, we also find the known results, right? That shows that the method is valid. So here you have your matched filter of a MIMO array with 3 transmit and 5 receive antennas. So this is the matched filter. Then we make a quadratic approximations, and based on that quadratic approximation, we find this half power beamwidth. And voila, you see, we find something meaningful, and we can also extend it to other types of MIMO arrays. We just change the parameters. Based on the parameters, you have different equations here, and it all seems to match. And then even more interesting, if you go to, for instance, the near field bistatic MIMO system, where here we have a transmit array, and in this case, here we have a receive array. We can also compute this ellipse quite accurately, which is nice because this gives us a way of computing accuracy analytically for a wide range of configurations. And from that, we can then also go to, we can compute resolution, but also from it, if you have signal to noise ratio, we can approximate the accuracy as well. Okay, cool. So this brings me to the next and the last thing I want to talk to you about. I want to extend all this to a more generic class of systems where we have a cell-free architecture. We have seen this plot already this morning. We have receive antennas, we have transmit antennas, we have user equipments that are using the same communication system and creating interference, and we want to characterize our radar performance. And here, for instance, I plot radar signal to interference and noise ratio. So this is just one result from the paper. This gives us the SNR. So if we would have a target at this location and this system, we could detect it with this signal to noise ratio, right? And the good thing to know is it's just a self-read system, similar to the one I showed before. But in the uplink, users are sending signals in the uplink. And that same uplink, some base station antennas pretend to be users and send the radar uplink signals. And the receiving base station, the red ones, they need to separate user signals from radar signals, and the radar signals they will use to resolve targets in the environment. So the processing looks a bit like that. I'll summarize it quickly. If you want more details, just go to the paper. There, everything is explained in all the details. So I have my received signal. And first I do channel estimation and I estimate my data, my payloads. And that I use to subtract user interference from my radar signal. Then from my radar, the residual radar signal, this white bar, I will decorrelate it because I have different transmit radar antennas. From these multiple signals, I will do my range Doppler processing. And these range Doppler maps, I will then also do array processing. Then I have distance, Doppler, speed, and angle. And then I'll send that through some threshold detection and come up with a target list. All the details of the algorithm and how to do it optimally and how to compute good ways of canceling interference as part of the paper. I'm not going to go into that now. So here you see one result that we can then compute. So here we have what we call radar coverage. Radar coverage means how much points of the space, at how much point of the space can we detect a target. And here is another parameter, radar SNR loss max. So this is how much interference we tolerate actually to our radar system. So the higher we tolerate interference, the lower the radar coverage is. But our user equipment will be happy because they will have more capacity. Yeah? So that's definitely a trade-off in the next system. And here you see, this parameter is how much radar access points we have, how much transmitters. So if we have 0 of them, then of course our radar coverage is 0. That's the easy part to understand. And you also see that if we have 5 of them, in this scenario, we have full coverage. So we need 5 access points to have full coverage. And then even with these 5, if we create more interference from our user equipment, nearby the user equipment that create all that interference, we will have coverage holes for our radar. That makes sense. Huh? So we can analyze the trade-off. And here you see another trade-off point. So for the same radar as in our loss parameter here, you see the spectral efficiency that we have for our users. And here this parameter is how much interference suppression I use, because I could use this system without interference cancellation. I can make it somehow maybe scalable by deciding which users I suppress interference for and which not. I don't need to do it for all of them to reduce compute cost. So here you see as function of how much users you subtract, what the spectral efficiency as function of the radar performance loss. And then you see if I subtract all my users, 40, I can have a pretty good coexistence actually, because I don't need so much radar performance while still having a very good spectral efficiency. But the cost is really compute cost, right? So it's quite complex. And here, if you come here to the complexity, I'm not going to go into the details of the complexity, but I'm going to summarize it very easy for you. So here, this line 1 is the cost to process one OFDM block, one FFT. And then you see that this UE cancellation is a bit more expensive. Okay, canceling interference is expensive. But this range Doppler and array processing, the green and the red ones, if you have a lot of radar transmitters, can become quite significant after a while. So what I said before on the full duplex part, if you do it here on OFDM with a lot of transmit receive antennas, it's not true anymore that the compute power is negligible. And what you should also be aware of the fact that typically we store many blocks, and the measurements that we showed, we had 640 blocks to see a trajectory of a can. That's a lot of data you have to store to do your processing. So not so easy to get this. And then the last thing I want to say, but I don't think I have a lot of time left. Actually, I lost track of time.
7 minutes.
What?
7 minutes around.
Okay.
That includes questions.
Yeah. Then the last thing I wanted to say is the impact of blockage, because I've made now an argument that self-free can be done, we have good radar coverage, etc. But most of the papers in the state of the art, they assume we have a line of sight between transmitter and targets. And if you have a self-free deployment, intuitively, I think your intuition can tell you already, like actually, if you compare a monostatic with a bistatic setup, which one do you think is better if you have a lot of blockage? The monostatic, right? Because the probability that you have a blocker and at least one of the two links in a bistatic is much higher than you have a blocker in one. Or even in a monostatic, here in a monostatic one, I can send the object if there is no blocker here. In a bistatic, I can only send the object if there's no blocker here and there is no blocker there, right? So it's more challenging. So we analyze this by taking also the probability of non-line of sight into account. And for that, we have some expression here that is used a lot in the UAV community for computing the probability that I have a line of sight with an altitude platform as function of alpha parameter that gives you, like, that represents how dense the city is, like how many buildings you have in the city. There's also some other parameters to represent how high the buildings are. So we have a similar model for our blockers. And based on that, you can see, so here M does not stand for multistatic, it stands for monostatic. This is a bit confusing. We should find two different M's to represent this. So this is the bistatic line of sight probability, and this is the monostatic line of sight probability. And you see here clearly that bistatic has a much lower line of sight probability. So the result of that is that if you translate this probability to the probability of target detection as function of how much buildings you have in your area, the message is that monostatic is better. So you see that monostatic always has a better probability of detection as compared to the bistatic. And if you have a lot of buildings in your area or blockers or cabinets or obstacles, the bistatic goes down quite fast. And it even holds if you would compare with a monostatic with only half of the number of access points, just to make it more fair. Even there you see that very quickly the monostatic is still better. So although we were initially very interested in the self-free for ISAC, and we thought it had a lot of benefits, and we were surprised that it works so well even with narrowband signals, from this analysis, we're a bit more skeptical, and yeah, we wonder if it will ever be usable, because I've had many discussions with my students that if you can detect the target, you can detect the blocker and do something about the blocker. But if you start developing the algorithm, it becomes very complicated very easily, and you need some, you need some ground truth also to know what is a blocker, what is a target, and it becomes quite complicated easily. Anyway, there's still a lot of challenges to deal with. Compute cost, memory cost, synchronization cost, dealing with blockers, and I think the biggest challenge is making the right trade-offs for the right use cases, right? And because you can easily make complicated systems, we want simple systems. And then if I still have a few minutes left, I will end with this. So we talked about requirements and use cases. I also think you see that there's a lot of going on, a lot of talk about sustainability these days. So therefore, I also want to make a case that whatever we do as academics and this community, we should try to think what it could mean for sustainability. So here you have a nice blog post written by Ericsson on this topic. There's not, of course, many types of sustainability. You have environmental sustainability, societal sustainability, economical sustainability. So all types of sustainability make sense. But I also would challenge you to think about it every time you work on it. And I think joint communication and sensing is obviously sustainable because you reuse and recycle and reduce equipment. And for me, that also means that you don't always necessarily need high-tech or terahertz, but it shows that you can do a lot also with low-cost systems. I started off with full-duplex sensing. The initial sensing tests we did there were doing Zigbee. It did 15.4, 2 megahertz, and actually we could do quite good sensing with that. We could also come up with use cases, for instance, good health and well-being, environmental monitoring, etc. But there's many of them, also societal and economical sustainability. And of course, we will have to translate all this to specs, because for now we only have the localization spec well defined, and there's a lot of work that needs to be done on how to measure all these. But I personally believe that to measure all these, we should get out of our comfort zone and work with the end users more. So for instance, a lot of our projects, for instance, the smartest project is a project where we really work on integrated communication and sensing with doctors in a hospital to see what it can mean for patients. It's a bit of effort because it's much more easy to work on accuracy and resolution, etc. But I think it's very valuable. And for instance, in this context, we're working on, so in my lab, we have now extended the same thing that you see here with the motion capture system. So you see here from the motion capture system, we cannot only measure RF signals, but I think you see what is this, right? Can you see it? It's one of my students running. So, and this will make it possible, I think, to do joint communication and human sensing in a way that can have real impact. Voila, get out of your comfort zone and meet the users. Thank you.
Okay, many thanks, Sofie. I think you already have your first question.
Actually, very loud noise. Thank you. So we can hear me in the back of the brother. More than a question is a comment, because you try to answer the question, is better to have a monostatic detection or a bistatic detection. And you replied based on the probability or line of sight. Actually, there are other factors that you should take into account. Radar cross-section target, whatever the target is quite different from the monostatic to the bistatic configuration, because generally the reflection are specular reflections. So if the radar sensor is transmitting here and is receiving the same position, so the power that goes back is very low. But if the bistatic receiver is here, then the power is much, much higher. So actually, maybe you can lose the probability of having the line of sight. This is true, but when you have the line of sight here, the power is much, much higher. So the probability of detection of the signal to noise ratio is much higher. So it is not just a matter of line of sight. You have to consider also other elements in your consideration. So that was just my comment. That's it.
Thank you. And do we have any questions, Richard?
First of all, thank you so much for the great presentation. Really interesting and a really great set of results. I just wanted to ask you one question. I know there was a block diagram of the processing, and you talked about interference cancellation on that flow chart. I don't know if you can go to it.
The flow chart of
the different processing blocks, and you had interference cancellation.
The spectral division.
This one there. So the interference cancellation. So this is then, correct me if I'm wrong, is this for multistatic or monostatic? This is multistatic sensing, right?
This is this is multi-static.
Right.
Many transmitters, many receivers, but they're distributed in a self-free way.
I
Yeah,
understand.
yeah.
So this parallel interference cancellation is cancelling out an uplink user for data away so we can pick up the sensing receive signal, right? Or not?
I'm sorry.
So the parallel interference cancellation, what are we cancelling here? Some uplink user which is sending data away from the sensing signal, or I wasn't clear what was happening and what were we cancelling here?
The users.
The
So
data users, right?
We have both.
So this means the sensing's performed in an uplink slot.
Yes, so the user sending an uplink. So there are many users. And there's only a few radar transmitters. So we need to cancel the interference from all the green users.
Okay, so this is the processing at the receiving node, which has got the uplink data users and also the sensing reflections coming through. Right?
These are self-free receivers. They all go together in a CPU.
Right.
Yeah.
And so you've got parallel interference cancellation here. It could be that the user data coming through, which is being picked up by that basis, maybe much higher than reflection signal. So could also consider maybe serial interference cancellation because there could be a big power difference between the two. That was just my only comment. Thank you so much.
Yeah, I agree that, but I also discussed this with so we came to it's worth investigating, but then of course you're never so
Because we don't know for sure. Yeah.
he wants certainty. So if you have errors in your payload estimation, it becomes difficult. Yeah, but indeed it would be worthwhile investigating. Also, if you go to this paper, it's a very interesting paper, but you'll see that the user channel is just the relay fairing channel, and the channel for the targets or just for the radars channels, or considering all the targets and the reflectors in the environment. I think it would become much more difficult to simulate it also because but I agree, it's worthwhile.
And it could also be that the uplink users that have got power control so that they receive at the same level at that receiving base station. So they'll kind of receive power irrespective of their distance would be the same because they've got uplink power control in the traditional system. So, but we could flip between serial and parallel depending on the, I was just curious. Thank you very much.
Control is essential here for the radar.
I mean, you mean for the user data? Yes, absolutely. Okay.
Yeah.
Got it. Thank you so much.
Yeah, but there are many variants possible, I agree. Yeah.
Thank you. I can see the question, but I think we better press on. I mean, you can catch up on the coffee break if that's okay. And sorry, I bet online